Hello, this is Dr. Strickland. In this video, we will investigate the second part of preparing buffers. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the more difficult things we will do together in class. Now, this is one of those buffer preparations that involves starting with one of the weak components and then generating the other one. In this case, we're going to start with the conjugate acid form and then add enough sodium hydroxide to change some of the conjugate acid into the conjugate base. Okay, so this is HEAPS, and I put the whole name up here and underlined the letters that end up in the abbreviation of the name. So 2-hydroxyethyl, there's the hydroxyethyl group. Piperazine is this 6-membered ring with 2 nitrogens, and then ethane and the sulfonic acid right there. And this is the acidic hydrogen that comes off to transform the conjugate acid into the conjugate base. You know, the name always goes with the uncharged form, regardless of whether it's conjugate acid or conjugate base. The pKa always goes with the conjugate acid. So this is what we got. Well, we know we've got 5 grams of this guy to start with and as much of this sodium hydroxide solution as we want. All right, so basically what we need to know is how much of this conjugate acid has to be neutralized. That's the big question. So I'm just going to put that here. Okay, so if we've got a neutralization reaction going on, we need a BCA table. So let's call this, let's just refer to this as HA and this as A- in our table. All right, so we've got our HEAPS, the conjugate acid, and we're going to have to combine it with an appropriate amount of sodium hydroxide to deliver enough hydroxide ions to convert some of the conjugate acid into the conjugate base until that ratio in the Henderson-Hasselbalch equation is just right. All right, so what do we need to know? Well, first thing we need to know is we need to know how many moles we started. Okay, so that'll be our first calculation. All right, so in the very beginning, we're going to have to add some number of hydroxide, but we don't know what it is. So let's just call it X. All right, and in the beginning, we have none of this. And as usual, there's no need to track, but if you wanted to, we don't need it. And so we're not even. So, you know, in any neutralization, it's going to go until the limiting reactant is all used up. In this case, the hydroxide is going to be the reactant. So it will decrease the number of moles of the conjugate acid and increase the number of moles of the conjugate base by exactly the same amount. So let's put number of moles HA before the neutralization. Then we need to find ratio of the moles of conjugate base to the moles of conjugate acid after the neutralization. And then we're going to need to calculate the volume of 626 molar sodium hydroxide required. Okay, that should do it. That'll give us a good strategy. And you know, as always, if you want to develop your own strategy, that is perfectly fine. All right, so let's see about this right here. All right, so of this conjugate acid comes from its mass. And you could look up the molar mass or figure it out from the molecular formula, but I think for the sake of time, I'm just going to tell you what it is this time. So for heaps, the molar mass is 238.30. This is grams per mole. Okay, so that gave me 0.02098 moles of the conjugate acid. Okay. 0.02098. Okay, so what we're after now is what is the value of X? Okay, because this is the number of moles of the conjugate acid form. This is the number of the conjugate base form after the neutralization. All right, so if we know the pH and we know the pKa of the conjugate acid, and we know the number of moles of the conjugate acid form, this is a Henderson-Hasselbalch problem. So the pH is 7.40. The pKa we found out was 7.56 plus the log of the conjugate base, which is X, over the moles of the conjugate acid, which is 0.02098 minus X. All right, so I want you to take a minute and work through the algebra and find out what the value of X is, and then come on back. All right, welcome back. And I got, you check behind me, I got X is equal to 0.008577. Okay, and so now the question is, what was X? And X is the number of hydroxide that are required, in addition to being the number of moles of the conjugate base that were produced. Okay, and so this is the useful relationship to us because now, if I know that, 0.008577 moles of hydroxide. So what do I need now? Well, I need that molarity. That's the 0.626 molar. So you can do it per liter and then convert liters to milliliters. Or what I did was I just, instead of writing 1 liter on the top, I just went ahead and did 1,000 milliliters. It's the same amount of volume. All right, so the moles cancel, and I got 13.7 milliliters. Okay, so I'm going to answer this question. Well, why don't you pause the video and write a statement. Pause the video, write a statement, and come on back. All right, welcome back. What I did, and yours doesn't have to be identical to mine, to make a pH 7.40 heaps buffer, add 13.7 milliliters of 0.626 molar sodium hydroxide to a solution containing 5.00 grams of heaps. All right, so that's the basic story on how to make a buffer by starting with one of the components and then generating the other one in the solution. If you have any questions, please send them to me.